Welcome to Homework Lib.
Part A of the given problem, the current passing through the material equals the potential difference between the plates divided by resistance. So I function of T, V function of T divided by R. The potential across the capacitor Vt is a Q of a T divided by C. Let's call this equation 1, where the capacitance is a Ck naught A divided by D. We substitute into equation 1, then I of t will become v of a t, that is r, so which is 1 over r d divided by kappa epsilon d a times a q dt, q function of a t. The resistance of a dielectric is given by Ohm's law, that is R is equal to resistivity Z d time area. From here we substitute, let's call this equation number 1. Substitute this into equation number 2 to simplify. I of a t will be q of a t times d divided by k epsilon naught a times the a rho times d. A will cancel out, so q of a t divided by k epsilon naught rho. Let's call this equation number 3. Then the current is the time derivative of the charge, so we can write I of t is minus dq of a t over dt, where the negative charge came from the fact that the charge on the capacitor decreases. So we substitute this in equation number 3. So minus dq over dt is equal to 1 over k rho times epsilon naught times q of t. Then q of a t divided by q is equal to minus dt over k sigma epsilon naught. We integrate both sides. Left hand side from q is equal to q naught to q, and the right hand side from t is equal to 0 to t. So q naught to q dq divided by q is equal to minus 1 over k rho times epsilon integration from 0 to t dt. Then integrating this and solving for qt, we get a q naught epsilon minus t divided by k kappa rho times epsilon naught. The current is the time derivative of this equation, that is I dt is equal to dq over dt, which is a q naught k rho epsilon naught times e minus t kappa rho times epsilon naught. The conduction current density equals the current divided by the area of the material. So JC is equal to I of a t divided by A. From here, substituting I of a t, we get a J of a C, which is a function of a time, Q naught divided by A, K rho epsilon naught times E minus T over K rho times epsilon naught, which flows from the positive to the negative plate of the capacitor. Part B. Now we need to show that at any instant the displacement current density in a dielectric is equal to the magnitude of conduction current density, but in opposite direction. So we have to show J d function of t is minus J of a c function of t. We start by writing E, electric field between the two plates, is given by E a function of t, q of a t divided by k epsilon naught times the area. The displacement current density is therefore J d of t is equal to k epsilon naught rate of change of electric field. From here, this will be k naught dq over t divided by k epsilon naught a divided by dt. This is above here. So this is equal to minus I of c function of t over a, which is a minus j c function of t. So we proved j over d displacement current is equal to minus j over c.